Oh, wait. How's it going?
Dr. John Wilson.
Yeah, one of my professors decided I think I'll be able to
Classic rides.
Oh, that's like questions about anything before we get started?
Yeah, can we have that?
Give a sec.
We have about 15 minutes. Make it 40.
Dr. John Catch.
I might have been moving at like 10 miles an hour until I got to me. It was really hard. Any questions about anything before we continue on with the stuff we were doing at the end of last class?
I do have a serious question. Are the tests, like, are you actually going to make it for 3 hours?
No.
Or is it meant for like an hour period?
Hour and a half.
That's a big question.
10-ish? No.
That doesn't
Do you like this question?
What's that? Well, like what questions? The questions that you're asking me? Sure.
Is it multiple choice?
No. Well, there'll be some that'll have the like actuarial problems, but not all of them.
Okay, I heard one ask, but do we get a guide?
I'll pick out some problems out of the sheets that I've handed out. Look at.
Same first letter, close enough. If we can't make it during the appointed test time.
Then you need to schedule one with me.
Can I schedule one for Friday?
We can talk about it outside of class.
Because I don't want to take that out instead.
For Friday, now we have
Well,
two.
but then you have two
I
on
take
Friday.
both in one day. It's pretty weak, dude.
That doesn't sound like a good reason.
Take it a day early.
Oh, anyway. All right. Let's go on and get talking about the stuff that we just started at the end of class last time with taking one of your events and breaking it into disjoint pieces to calculate its probability. So going back to that dice rolling problem, that was 4.2 in this sheet that I handed out last time. I want to move down to 4.4, same sheet, but 4.4 has the exact same setup as 4.2, but it's asking a slightly different question. So remember in 4.2 we had I don't know why it's always urns that you're drawing things out of. We have the urn that has 4 dice in it. 2 of them are normal dice. 1 has just the evens on it, and 1 has all 6s on it. In this particular case, it tells you that you're going to randomly select a die, and you know that when you roll the die, it lands on a 4. It wants the probability that the die, the even die was selected. So we want, from this setup, we want the probability that the even die was selected given a 4 was rolled. Right? It tells you that the 4 was rolled. It says calculate the probability that something else happened. That the even die. So we're given information, so we know we're calculating conditional probability. Okay? All right. If we use the conditional probability formula, what does it have to equal? Just according to the formula, not with any numbers right now, but just writing out the conditional probability formula, what does that have to equal? Okay, so in this case, you're using A and B. So what was your A and what was your B? Okay. Good. Oops. And so like Marshall said, if you have the probability of A given B, your top is the probability of A and B, the bottom is the probability of B. Like I mentioned before, I like to think of this as kind of your fraction bars that reminds you of which one should go on the bottom. Right? I think this is a fraction bar, this would be the bottom, so it goes up bottom. That's how I first work. All right. So now, when we calculate this probability, the top is not too bad because we can do the top just like we did before, right? Because it's an AND probability. I need to pick out the even die, and then I have to roll the 4, right? Are those independent events, though? Is picking out the even die and rolling a 4, are they independent where I can just take the probabilities and multiply them together? No. It's conditional, right? I have to pull out the even die, then I would have to roll a 4 given that I have the even die, right? Okay. So on top, if I'm just writing it out using the words, on top you would have probability of even die, that you drew the even die, and then you would multiply by the probability you roll a 4, given that you drew the even die. Because remember, from your conditional probability formula, you can always rearrange your equation, right? We said probability of A given B is probability of A intersect B over probability of B. But I can solve that for the intersection, right? Right? So in this case, if we use our, well, it doesn't matter what you use for A and B. I could also get this as probability of A, probability of B given A. Either way works, right? So in this case, I'm using the second formulation of this, right? Probability that we rolled, picked the even die, probability that we rolled a 4, given that we had the even die. Notice when we have the AND probability, it's still multiplication, but they're not independent. I have to use the conditional probability for that second factor. Right? It's not just probability of A and probability of B multiplied together. All right, on the bottom, well, there's a whole bunch of ways that you can get a 4, right? All of them depend on what you pulled out, right? There's different ways to get a 4. How could you get a 4?
Pull out one of the regular dice.
You pull out one of the regular dice and roll a 4, or the even die and roll a 4, or, well, then you roll out the other die, you get a 0, right? You can't roll a 4, right? So there's 3 different possibilities, right? We've got those 3 different disjoint possibilities. You could do 4 rolled, or I guess I should write it the other way around. Regular die and 4 rolled. Oops. You could do even die and 4 rolled. Or you could do the 6s die and 4 rolled. We've broken it up into 3. I know that last case is impossible, but it's still one of the 3 cases we could have for pulling out a die, right? We've broken up the event, rolling a 4, into 3 disjoint pieces in this case, right? Right? Just like when we talked about right at the end of class on Monday, the same idea, right? Taking the event of rolling 6 twice and breaking it up into 3 disjoint pieces. Since they're disjoint, what would I do with these probabilities? Add them, right? We add them together. And then we can compute all of them using conditional probability like we have on top, right? Notice on top we had exactly one of these cases, didn't we? Even die and 4 rolled. And so that we can calculate that as even die times even die, or 4 rolled given even die. Right? So this one would be regular die times 4 rolled given regular die. 6's die times 4 rolled given 6's die.
Did the problem say there were 2 regular dice?
Yeah.
So do we just put 2 in front of that?
Well, we'll factor that in with the probability. Because all you can draw out is a regular die or an even die or a 6 die. All right, so let's think about what the numbers are now. What's the probability that you pull out an even die? 1/4, because there's only 1 out of the 4, right? Given that you've pulled that die, what's the probability that you roll a 4 now? 1/3, good. So your numerator is 1/4 times 1/3. The denominator now has 3 pieces. We've got regular die and a 4 was rolled. Well, what's the probability that you drew out a regular die? That one's 1/2, right? Given that you pull a regular die, what's the probability you draw a 4, or roll a 4, sorry? 1/6. The second part was even in 4 roll. We just did that a minute ago, didn't we? That's a 4th times a 3rd. We agree? The last one, and I know it's impossible, let's just do it. Probability that you pull the 6's die? 1 out of 4. Given that you've pulled the 6's die, what's the probability you roll a 4? 0, yeah. And then we can go through and do the arithmetic here. Well, you get a 12 over 2/12. So you get a half. Is that right? If I did my arithmetic right? Does it make sense that it should be an even shot that you roll the 4? Or that you pull out the even die given that you roll the 4? Well, you're twice as likely to pull out a regular die than you are the even die, right? But the even die has double the 4s. So if you know you've rolled a 4, it's a 50-50 shot that you pulled out a regular die or the even die. This is a special case of what we refer to as Bayes' theorem, and I'm not going to write down the theorem because I'm never going to make you write down what the theorem says. But let's talk about what we've done. Let's just think about the process we went through because that's the important part of Bayes' theorem. Okay? For Bayes' theorem, we started with a conditional probability, right? Notice that we've converted this problem with this conditional probability and made the condition part of what we were trying to figure out the probability for, right? We flipped what the given, basically we flipped the given, right? Notice the top, we were given the 4 was rolled. The top now is we were given the even die was proved. We flipped around what the conditional is. And we did that because it was easier to calculate it that way. Okay. So instead of, well, that's what Bayes' theorem is all about. Instead of using this as our conditional what's given, we flipped the problem and made it what we're trying to calculate the probability of given the other information. So rather than stating what Bayes' theorem is, which you can see in the book, I'll point you to the page. But I don't see the point in trying to memorize it because you're just going to go through and do the problem. I'll get there. No problem. Well, it's stated on the bottom of page 46. But again, the whole idea is to flip the conditional around so that you can actually calculate the probability. All right, so let's do another problem like these. Let's look at, are there any questions about this one before I go on to another one? I guess I should ask that first. See how these work. All right, let's look at, this is 4.1. So this was not actually, well, it's not doing the conditional part, but it gives you an idea of what we're talking about. So 4.1 says that 10% of employees, oops, I gotta spell, in the first 5 years earn $100,000 or more. And then 20% of employees past their first 5 years. Oops, should say the word first in here. This is why I hand out the sheets, so I don't have to write all these things. Past 5 years earn over $100,000. And then it tells us that 13% of all employees earn more than $100,000. All right, let's see if we, before we go into what the question asks, let's see if we can formulate these statements into symbols. So let's say that the event A, just for lack of a better letter, is employees, oops, in the first 5 years. And event B is employees earning 100,000 plus. The third statement is probably the easiest one to formulate to start with. The third statement says 13% of all employees earn 100,000 plus. We think about it as a probability. What does that third statement say? Probability B is 0.13? Yeah. Good. That's exactly what that says, right? It says 13% of all employees earn $100,000 or more. So that's exactly what B says. That's the event of employees earning over $100,000. Okay? So far, so good? All right. So let's look at the first statement. It says 10% of employees in their first 5 years earn $100,000. How do we convert this to a probability statement?
Could we say probability of B given A is 0.1?
Good. Yep, so we know the probability of B given A is 0.1. Good. So given that you have an employee, so that's the given part. It says 10% of employees in their first 5 years. Right? So the employees in their first 5 years is the given information. The additional is, given that, 10% of them earn $100,000. Okay? So you convert that to that conditional statement. How about the second one? the 20%, this second statement. I only gave you an A and a B. We still should be able to do it using those letters and not have to introduce a new letter. Yeah.
Probability of B given A complement.
Good, yeah. Should be 0.2. Good. If we think about it in terms, if you want to think about it in a picture terms, here's your A, here's your B. The first statement says 10% of employees in their first 5 years earn $100,000. All right, so if this is your $100,000 circle, what that first statement says is that this region in here, that shaded region is 10% of the total. So here would be your total part, this way, right? What the first statement says is that, write it this way, I'm using another color here. This first statement says that 10% of the total of the circle is equal to that smaller region. Just using it from the picture. So that first statement says we're cutting down the whole region into this smaller circle. And it's saying that this part here, this little sliver, makes up 10% of the whole circle. That's the first, and that's why it's a conditional probability. For that first statement, we're not considering anything outside of the red vertical line region. Okay. In the second part, notice it's outside of that circle, right? Everything outside of A would be represented by this region out here, right? And what it says is that this part of the circle of B is 20% of all of the region that's outside of the circle A. I'm not sure if the picture helps, but some people see the picture a little bit better. Okay. So for the first statement, you're only living in the circle A. For the second statement, you're only living outside of the circle A. Neither of those two statements are the entire sample space. It's conditional probability. Does that make sense? All right. So notice that all we've done right now is set this up. What does the problem actually ask? It wants probability of A, right? That's the percentage of employees in their first 5 years. All right. So how are we going to get at that information, thinking about the way we have to split things up again? Okay, well, we can find the probability of A complement, we would have it, right? We could do it that way. How are we going to get there?
Rewrite probability of B given A complement.
Okay.
Probability A intersect. Probability B intersecting probability.
Okay. Probability.
Probability of A complement.
Good. Okay. What else can we do?
Would you like to say the function?
Okay. This? Is that what you said?
Yeah.
Oops.
Those, like, wouldn't one be equal to 1 minus the other?
Which ones you're talking about? The ones that are on the left-hand side? Or the denominators on the right-hand side?
Well, we've got A and A complement.
Yeah.
So if one's the number, one's the opposite of it. So we're going to be able to say something.
So these two definitely are, if I add the denominators here, those definitely have to add up to 1. But unfortunately, these two don't, the way they're written. That's kind of the idea behind this problem, is you rearrange some things. These two aren't because of the way it's written, my complement's in the wrong spot. If it were the other way around, it would work. So can we get it written the other way around? Ask that. So we know that the probability of B intersect A complement is definitely a probability of A complement and this probability of B given A complement, right? But what else is it equal to? What's the other way around we could write it? Okay, good. You'd absolutely do that, right? We agree? And we could do the same thing for the B intersect A. We would have that, but it's also, so this first statement is just rearranging the fraction here, but it's also probability of B, probability of A given B, right? That's just rearranging our conditional probability. Now, let's think about these two now. These two probabilities here, underline them. These two probabilities are stated better. So think about it this way. Given that you're in B, the first one says that you're not in A, the second one says that you are in A, right? Well, either you're in A or you're not. So those two things take up 100% of the possibility given B, correct? So from those two things, we definitely know that the probability of A complement given B has to be 1 minus the probability of A given B. Because if you're in B, you're either in A or you're not in A. It's the only possibilities. You don't have any other choice. So we're able to plug these things in now. So for that purposes, we could have, so we've got probability of B intersect A complement would be probability of B times 1 minus the probability of A given B. And we would have the probability of B intersect A is probability of B times probability of A given B. So that's one good thing about switching around the problem. One good thing about switching around the problem is, in that first piece of information, I no longer have a complement in it. Right? In the first piece of information, I no longer have an A complement in it. Another reason why this is beneficial is these formulas now have what in them? What's the first factor? Probability of B. Do we have a number for that? Yes. Yeah, right? We know probability of B. So this would be 0.13. Oops, 0.13.